Hey folks, today's topic is operations with complex numbers. So we have to introduce, well, it shouldn't be an introduction. You should have seen these last year. But we have to review a little bit of what is a complex number. What do we mean when we're talking about a complex number? So we're going to do a definition in a minute, but I want to start off with, get us in a spot where we already are familiar. Square root of 49. What's the square root of 49? Is it plus or minus or just 7? It's just 7. Remember, it's when you write the square root. If the problem comes with the square root, the answer is just 7. If it doesn't come with the square root and you have to add a square root to solve it, then we have to do plus or minus. All right. Mathematicians came along. Somebody figured out they discovered this idea of square root, this operation of square root. So life was good. Yay, yay, yay. And then all of a sudden they got to these problems that weren't nicely square rootable. They got to situations like square root of negative 49. And nobody knew how to handle it. So for a long time, we just said no real solution, no real solution, no real solution. Well, this guy by the name of Cantor came along, I think it was Cantor, came along and said, well, I'm going to work with these numbers. I'm going to create a whole new number that's called I, so I can handle these square roots of negatives. So let's define what he was talking about when he created imaginary numbers. So definition. A complex number underline complex and number is a number of the form a plus bi, comma, where a and b are real numbers and I is equal to the square root of negative 1. So Cantor said, I don't want to deal with this negative. So I'm going to create this new symbol that's going to take care of the negative for me. Now, we've already practiced breaking up square roots, so we should feel pretty good about how to break something up. So what I'm going to do is I'm going to take this root and I'm going to separate it into two pieces. I'm going to break it up into the negative 1 times the 49. Now, that's still worth negative 49 underneath the root, but the way that I've written it is I can now have stuff escape the root. So the square root of 49 becomes a 7, and then the square root of negative 1 we have defined to be this letter I. So that's Cantor's idea. He said, well, at least now I can do some algebra with these numbers if I come up with this symbol I that represents negative 1. He didn't have the symbol. I think Euler was the one who came up with the I to represent imaginary. Now, they're imaginary not because they don't exist. It's because the first set were called real, and Euler thought, well, what's the exact opposite of real? It would be imaginary. All right, let's take a look. So let's break down some numbers that aren't quite as nice. So let's try the square root of negative 75. So right away, 75 isn't a perfect square, so this is where we go back. Something else we did at the very beginning of the year, section 0.3, I think, where we simplified roots. So I want to find a perfect square that goes into 75. Hopefully you figured out that 25 is the biggest perfect square that goes into 75. So I'm going to split this up into a negative 1, a 25, and a 3. If you multiplied all that together, you would still get negative 75, so this is still worth the same stuff. But now things can escape the root. I always take the nicest thing out first. So 25, when it gets square rooted, becomes a 5. The negative 1 can get square rooted and becomes a I. And the 3 is not a perfect square, and it can't break down anymore into perfect squares, so that's the best we can do. All right, let's have you try one. Yours is the square root of negative 72. Pause it. Try to clean it up. Okay, this one's a little bit sneaky because 72 has so many perfect square factors. I don't know why I write 74. 72 breaks into 4 and 18, then 9 and 8, but 36 and 2 is the best choice. So you always want to try to pick the biggest perfect square that works. If you did, let's say 9 and 8, that's fine. You just got to break down 8 again because 4 goes into 8 and 4 is a perfect square, so you'd have to clean it up further. So I'm going to break this up into negative 1, 36, and 2. Take out the nicest piece first. The square root of 36 is 6. Square root of negative 1 we have defined to be I. And 2 is not square rootable, nor can it be broken into something that's square rootable. So this is the best we can do. All right, so there's kind of the introduction on how I's work. I would like to go through a little chart here talking about evaluating different exponents of I. So let's take a look at, so what is I? I is equal to the square root of negative 1. What is I squared? Well, I squared would be the square root of negative 1 times the square root of negative 1. Well, what's going to happen to those square roots? They're going to cancel out, and you're going to be left with just negative 1. So I squared turns out to be negative 1. What's I cubed? I cubed would be I times I squared. So negative 1 times I would turn out to be negative I. What is I to the fourth? I to the fourth would be square root of negative 1 times square root of negative 1 times square root of negative 1 times square root of negative 1. So these two would come together and make a negative 1. These two would come together to make a negative 1, and negative 1 times negative 1 is 1. Now what's kind of cool about the I, the number I, is as we keep going in this progression, what's I to the fifth? So that's like taking I to the fourth and multiplying it by I. So what's 1 times I? I. What's I to the sixth? That's like taking, let's pick two nice ones. That's like taking I to the second and I to the fourth. What's negative 1 times 1? Negative 1. I to the seventh would be, let's say, let's take I to the sixth times I to the first. So that would be negative I. I to the eighth would be I to the fourth times I to the fourth. So what's 1 times 1 is 1. Look at this pattern. So I is I. Then it goes negative 1, negative I, 1. I, negative 1, negative I, 1. Guess what I to the ninth is? I, and then so on, etc., etc., etc. All right, so now the rest of today's notes are just doing operations on those imaginary numbers. So, sorry, complex numbers. So let's start off with adding and subtracting. So this is the complex number 3 subtract 4i plus the complex number negative 1 plus 2i. This goes exactly how you would think. You'd combine like terms. So 3 plus negative 1 is 2. Negative 4i plus 2i would be negative 2i. We can't combine those because they're unlike terms, but we could combine some of the like terms up here. Next one you probably could do on your own, but let's just do it together. 3 take away a negative 1 is 4. Negative 4 take away a 2 is subtract 6i. So why don't you pause and do this last one that has an add and a subtract rolled together. All right, let's see how you did. So I can just go through and put all the constants together. 3 plus 4 is 7. Take away 10 is negative 3. 2 plus negative 1 is 1. Take away a negative 3. 1 plus 3 is 4. Addition and subtraction of complex is pretty straightforward, just like multiplication is pretty straightforward too. I mean, pretend like those were x's. What would you do instead? You distribute, just like, yeah, you just guessed. So it's pretty straightforward. So let's go ahead and distribute these. So I'm going to do 2 times 4 is 8. 2 times 3i is 6i. Negative 1 times 4 is negative 4i. Negative I times 3. Now this is where it gets a little bit tricky. A negative times a 3 is a negative 3. I times I is I squared. Now, we talked about I squared already. I squared is the equivalent of negative 1. So anytime you get an I squared, I recommend just crossing that term out right away and then changing the sign. Because if this is worth negative 1, that negative 3 is going to get multiplied by a negative 1 and become a positive 3. And then now I can combine like terms. This is an 8. The I is gone. So this is just 3. 8 plus 3 is 11. Then 6 take away 4i is 2i. Let's try another one. Ooh, this is a little sneaky. Remember, 5 minus 3i really means 5 minus 3i squared, really means 5 minus 3i times 5 minus 3i. Now I would start to distribute. 5 times 5 is 25. 5 times minus 3 is minus 15i. Minus 3 times 5 is minus 15i. Now, this is the one you got to be careful. Negative 3 times negative 3 is positive 9. I times I is I squared. But I squared really means negative 1. So I'm going to kill the I squared, but I'm going to switch the sign of that term. So that's now a negative 9. 25 take away 9 is 16. Minus 15 is minus 30. Let's have you pause and try to do the next two on your own. All right, let's see how you did. So this one's kind of nice. You can just distribute. So I'm going to take 8i and distribute it to both of them. Now usually we like to, well, I'll just distribute first. 8i times 4 is 32i. 8i times negative 3i is negative 24i squared. I squared instantly tells me that's a huge clue. That means that I'm going to cross it out and switch the sign. And then I want to put, usually I like to put it in a plus bi format. So I'm going to push the constant number first, 24 plus 32i. And then example 7, I'm going to start distributing again. Something interesting happens with these. So 2 times 2 is 4. 2 times negative 4i is negative 8i. 4i times 2 is positive 8i. Positive times a negative is a negative. 4 times 4 is 16. I times I is I squared. But anytime we see I squared, we kill it, cross it out, and switch the sign. So I'm going to cross this out. I'm going to switch the sign to a plus. So we got 4 plus 16 is 20. And then negative 8i plus 8i adds up to 0i. So we just get 20. And these are special complex numbers. These are called conjugates. These are called conjugates. And conjugates are nice with imaginaries because look at, we had stuff with I, and what do we have at the end? We don't have any I's. So that's the idea of a conjugate. If you ever want to cancel out an I, we have to cancel out with these things called conjugates. And that's exactly how we need to do division. So division, unfortunately, is not like addition and subtraction. You can't just divide like terms. We have this quantity divided by this quantity, and so we can't just do the pieces. It doesn't turn out to be the same. I mean, eliminate the I and see if it will work, and you'll see quickly that it won't. So what we're going to do instead is we're going to kill off these i's on the bottom. And the way I'm going to kill those off is I'm going to multiply by the conjugate. So I'm going to times by the conjugate of the denominator. So 4 plus 2i. Now we just did this one, or one similar to it. Sorry, not exactly the same, but similar. So you're going to notice that when I distribute this, the i's are going to be gone on the bottom. That's the whole point. That's what we want to do. We want to get rid of any i's on the bottom. Now the problem is if you multiply the bottom by 4 plus 2i, we got to multiply the top. by 4 plus 2i. Notice we only did the conjugate of the bottom. So I want to leave a little note there. Mult by conjugate of denominator. So I multiplied by the conjugate of the denominator. Now watch what happens. Now the top is going to get messed up. That's okay. 2 times 4 is 8. 2 times 2i is 4i. 3i times 4 is 12i. 3i times 2i is 6i squared. Now before I go any further, I'm going to stop here. And I'm going to cross this out and change that to a negative so I don't lose track of it. Over 4 times 4 is 16 plus 8i minus 8i minus 4i squared. As soon as I see it, I'm going to cross out the I squared, switch the sign. And now look what happens when I combine like terms. 8 take away 6 is 2. 4 plus 12 is 16i. Over 16 plus 4 is 20. And then 8i take away 8i is 0. So now we don't have an I on the bottom. This is what we consider a cleaned up, well, not quite fully cleaned up yet, but this is more cleaned up than what we had before because we don't have any i's in the denominator. Why is this not considered fully cleaned up? Because everything that's free is divisible by 2. So my best full credit answer would be 1 plus 8i over 10. Now you might see the answers written a little bit differently. Hopefully you see that they're pretty much the same format, just a different way of writing it. So the other way you could see your answer is like this. 1 over 10 plus 4 over 5i. So I broke up 1 over 10 and then I did 8 over 10, which reduces. So this answer is okay too. I don't care which way you do it. I think on the answer key, I left them all like this. Okay, I'm going to encourage you to pause here and try to do the next one on your own. Let's see how you did. I want to multiply by the conjugate of the denominator, so that's minus 3 minus 2i. So the conjugate is exactly the same as the denominator with a different sign in the middle. I don't know if I said that enough up here. So I leave the negative 3 the same. I switch the sign in the middle. That's the only way you're going to get stuff to cancel out. Now the top is going to become a mess. Minus 12 minus 8i plus 3i. Okay, a negative times a negative is a positive. 2i times I is 2i squared, but I've got an I squared, so I want to kill that off and switch the sign. So that's going to become a negative. Over, this is where the math of magic should happen. Negative 3 times negative 3 is 9. Negative 3 times negative 2i is positive 6i. 2i times negative 3 is negative 6i. Positive 2 times negative 2 is negative 4. I times I is I squared. But I squared really means negative 1. So I can switch the sign. And let's see what we have as our final. Minus 12 minus 2 is minus 14. Minus 8 plus 3 is minus 5i. Over, okay, 9 plus 4 is 13. 6i minus 6i is 0. Here we go. Notice this time I couldn't clean it up. 13 is prime. 5 is prime. So there's nothing that goes into 5 and 13 or 14. So this is how I would leave it. If I did want to write it the fancy way would look like negative 14 over 13, subtract 5 over 13i. You could write it that way if you wanted to. All right, folks, that's it. Good luck.